Okay, so welcome back. We are now on lecture number 8 or 9. I think 8. Yeah, I think 8. Right, end of the 4th week, and we are working on the chapter 4, chapter 5 PowerPoints, and we. Which slide did you say we were on? 15. Yes, measuring linear association, correct. Okay, so we're at the point right now where we understand what a scatter plot is. We have 4 factors when it comes to scatter plots that we use to get a sense of what's going on. Can anyone remind me what the 4 factors of a PowerPoint are? The 4.
One could be.
Sorry,
I was saying one was whether it's linear or not linear.
Linear or not linear. Okay.
Strong or weak?
Strong. Well, strong, moderate, or weak. Direction, whether it's positive or negative. And what was the 4th consideration?
Outliers.
Whether or not there's any outliers. Correct. Okay. So those are the 4 qualities. But then we also saw the example of a zoomed in version of a scatter plot, which made it difficult to determine whether or not it was strong, moderate, or weak because the scale. So we want to have a mathematical measure of linear association. And to that end, we have the slide 16, which is measuring linear association. So the first thing that's important to realize is that this equation only tells you whether or not there is a linear association. It gives you no information at all about just having an association. So if it's a quadratic association, if it's a logarithmic association, if it's an exponential association, if it's any other type of association besides linear, then this equation will give you nonsense. It will not give you a value that will necessarily be close to the true value. It can only tell you whether or not it's linear. So we call it the correlation R, and R could be positive or negative, and as such, R will answer the question about whether or not it's positively correlated or negatively correlated. A positive R means it's going upwards. A negative R means it's going downwards. We also have the direction. Well, I just told you the direction. We also have the strength. So we're going to see certain R values tell you that it's strong. Certain R values tell you that it's medium or moderate, sorry. And certain R values tell you that it's weak. So as we're going to see, R gives us all 3 things, right? If it's strong linear, then it basically tells you that it's linear. So it's giving you the fact that it's linear, it's giving you the strength of the linearity, and it's giving you the direction. So it's really doing a lot. It can't tell you about outliers directly, but as we're going to see, if you think something is an outlier, then you can compute the correlation with and without it and see how much of a change there is. And that'll give you some idea about whether or not it was an outlier. But what is the formula? So it's a very complicated, Brielle, you're here. Did you get my email? I just sent you an email about 5-6 minutes ago. Did you get it? So you're all good from here on out the rest of the semester? You'll be okay? Okay, so I'm gonna mark you as presence.
Okay, thank you.
Okay, so let me just do that quick. Oh, wrong one. Give me 1 second, everyone. I'm sorry. Let me just do this quickly before I forget. And speaking of which, is there anyone who has their attendance from a previous day not correct, like you were late but not absent or something of that nature, and I haven't corrected it yet? If that's the case, let me know, and I will correct it immediately. But nevertheless, so on slide 16, we have the formula for the correlation. It's a very complicated looking formula. So if only there was a way of doing it that did not require such a complicated formula. And is there one? Is there one? Yes, there is.
Crunch it.
Crunch it or a calculator. But what if you're stranded on a desert island and you don't have either of those 2 things and you have to measure the correlation? Stranger things have happened. Then the formula is given on slide 16. So let's just quickly go over it, even though we're not going to really get into it too deeply, since we can do it with technology. But you see, like the standard deviation, we divide by n minus 1, not by n. So it's 1 over n minus 1 is the leading term that is factored into the entire thing. And like the correlation, we take each deviation and we subtract the average and divide by its standard deviation. So x1 minus x, oh, that's a mistake. Anyone see the mistake in the PowerPoint, the typo? Who here can spot the typo? You've never seen the formula before, but there is something that should stand out as, wait a second, that doesn't make any sense. What is it in that formula that's the typo?
Is it the S of Y and not S of X?
Yes, so which one is wrong? There's a lot of them. Which one is wrong?
The first one,
The first one should be
S of X.
S sub x, right? The x's go with the x's. The y's go with the y's. It seems very straightforward. Yeah, the first one, the S sub x. It's x1 minus x bar over S sub x, y1 minus y bar over S sub y. Do that. Then do x2 minus x bar over S sub x, y2 minus y bar over S sub y. Do that. Do it for the third, do it for the fourth, do it for the fifth, all the way to the last one. Add them all together, divide by n minus 1, and you get this correlation. Now, it's a lot of work, which is why we really don't want to do it, especially if there's a lot of data points. But notice that it requires us to find first x bar and y bar and the standard deviation of s, s sub x, and the standard deviation of y, s sub y. You have to know those 4 things, and of course how many terms there are n, and only then can you calculate r. And we're going to have some properties of r that we'll get to in a minute, but for now let's turn to the next slide. The sample correlation, right? It measures the strength of the linear association between 2 variables. Again, it could be a non-linear association, but this will never tell you. This can only tell you how strongly linear it is. So some facts. 1, it's always between -1 and 1. Okay, if you ever calculate a correlation and you get something that's not between -1 and 1, you made a mistake somewhere, because mathematically it is impossible. It has to be somewhere between -1 and 1. That's step number 1, or property number 1. Number 2, the sign. If it's positive, what does that tell you what the direction of the linearity? It's going upwards. If it's negative, what does that tell you? That it's going downwards. Seems very reasonable, correct? Okay. Property number 3, the magnitude, the value, if we ignore the sign, is always between 0 and 1. If it's close to 1, it tells you that it's very strongly linear. If it's close to 0, it tells you that it's basically nonlinear or very weakly linear, with numbers in between being moderate. Okay? So for example, r equals -0.4 conveys a negative relationship. It's going downwards with strength 0.4. And as we're going to see, an r value of 0.4 is essentially extremely weakly linear, as we're going to see in a minute. But are there any questions on that so far? All right, so let's turn now to slide number 18. Okay, so slide number 18 gives us some guidelines for taking the value of r and being able to interpret it in terms of the strength of the relationship. So it says if you get an r value whose absolute value, if we ignore the sign, is between 0 and 0.1, there's basically no linear association. It's just a blob of points. Okay, it's just nothing there. If it's between 0.1 and 0.5, it's weak. It's there, but it's weak, all the way up to 0.5, which is a significant amount of the difference between 0 and 1. You're basically saying half of the difference between 0 and 1 is considered weak. 0.5 to 0.8 is moderate, and 0.8 or higher we would say is strong. And of course, 1 is just perfect. It lies perfectly on a line. Does that make sense? Again, these are arbitrary cutoff points, right? If you get 0.5001, you can't say, oh, it's moderate, and then 0.499999 is weak, because, I mean, they're essentially the same thing. So these are guidelines rather than hard, fast rules. However, as far as this course is concerned, they are hard, fast rules. So if you get 0.5001, that's moderate. And if you get 0.4999, that's weak. Does that make sense so far? Seems good? I hope. Okay, good. So let's turn now to slide number 19, sample correlation continued. By the way, why is it called the sample correlation? Because we're only taking a sample. We don't have the entire population. If we had the entire population, it would be the population correlation, which we don't know or will never know because we only take samples. So if the points of a scatter plot all fall on the same line, it is a perfect correlation, R equals 1 or R equals -1, depending if it's positive or negative. Okay? If the points form a directionless cloud, so if you look at the slide in the bottom, I mean, if you said, oh, no, it's a line, I'd look at you like you're crazy. It just looks like a blob of points, right? In that case, the correlation between X and Y is 0. Does that make sense so far? Yes, hopefully. So let's turn now to slide number 20. As an example, it says card data. The following table displays sample data for 5 cars of comparable type. Mileage and selling price. Now, if we just look at the scatter plot there, would you say that there is a linear relationship between those 5 points?
Yes.
Yes.
Certainly looks that way, right? Certainly looks that way. And would that be positive or negatively linear?
Negative.
Yeah, negative, that goes without saying. The only question is how strong it is. And it certainly looks fairly strong. In fact, except for that one little guy in the bottom, you know, in the middle, by 25, 7.6, it almost falls on a straight line. But remember, looks can be deceiving. And therefore, now that we have a mathematical measure of correlation, we should always use it. So we don't have to go through all the calculations like they did, but we should see what they did so we understand it. First, they took all the X values, the mileage, and they calculated X bar and S sub X. Would you mind? They found X bar and S sub X, correct? Then, 1 second. I have a text here. I'm sorry for being late, but I'm here. I was trying to, well, yes, I will mark that you are late, unfortunately, but you are here. So I just fixed it. Welcome to the party. Hope you brought some pie. Anyway, so we have X bar and we have S sub X, correct? Then we have Y bar and S sub Y. 4 of the 5 things that we need. We also need N. What is N in this example?
Number of cars.
The number of data points, the number of cars, 5. Someone texted me 5, correct? And then they put it into the formula. They did all the math for us. They actually used a different version of the formula, which if you look at the previous 3 slides back to 17, they came up with an alternative, some alternative formulas. But at the end of the day, because we're going to use a crunch it or a calculator anyway, I'm not going to take the time to really go through why all those different formulas are valid. You're not going to be asked to do it by hand. But nevertheless, they did it, and they got negative 0.96. Now, the fact that it's negative, of course, is very reasonable. It should be negative. 0.96 tells me what about the strength of the correlation?
It's strong.
It's very strong.
Very strong, right? It's very strong. And it's not linear. It's not perfectly linear, of course. That one guy there, and even the 32 looks a little off. But you see it's very strong. So we have a very strong linear relation, okay? So let's now turn to slide number 21. Regression analysis. This is the other half of the coin, right? The first half was correlation, and the other half is regression. And now when I look at the textbook.
Professor?
Yeah.
Can you show us how to do this on Crunch It?
That's a great idea. That's a great idea. Let's load up Crunch It and see if we can figure out how to do this. So here's Sapling. I'm going to share my screen. So here is Crunch It. And let's start by putting in our data. Let's go back to, okay. So let's take a look if we can figure this out. So Let's see. How do you put in data? Enter data, double
If to
click.
double click, yeah.
All right, 3.5. Sorry, not 3.5, but rather 35. 35, 22, 32, 18, 25. And then we have 7, 8.5, 7.2, 8.9, 7.6. Right, so we have our 5 data points, correct? So let's now see. It's not going to be a distribution. Scatter plots. So let's try scatter plots. So x is variable 1, y is variable 2. So let's see what pops up here. So here's my scatter. Let's raise this up a little bit. Here's my scatter plots, but there's no information there. So let's take a look. Is there a way to add stuff? Points, x slope, this. Okay, that's not what I want. So what else can we do here? Oh, here's another correlation on statistics. Variables 1, variable 2, calculates. Hey, look at that. So we see that the correlation is negative 0.9599, which matches what's in the book, right? You all saw that, I hope? You can see what I'm looking at?
Yeah.
Okay. So FYI, I never did this on Crunchit before. I just experimented, and it wasn't that hard, right? So hopefully you guys will do the same thing, where sometimes if you don't know how to do something on Crunchit, you just experiment. And thank you. And Crunchit is a lifesaver, right? Crunchit is pretty amazing. So I'm looking at the textbook, and chapter 4 is on scatter plots and correlation, and chapter 5 is on regression. So what button do you press to see the number? I'm going to share again. So let me share again here. So I'll erase this. So what I did is I put in my data. I went to graphics for the scatter plot, and it popped up, but I didn't really need to do that. I just need statistics. And then I went down to correlation, and I clicked correlation, and I wanted to correlate my 2 variables, variable 1 and variable 2. And then I calculated, and there it is. It just pops up. Uh-oh. Whoa, what did I just do? No, I don't know what I just did. Oh. Okay. Oh, I see what I did. So there you go. All right, don't need 2 of them. But it's kind of cool because you can have multiple variables and you can correlate any pair of them you want. We only have 2 in our example, and we see a very strong correlation between them. But in general, you can have lots and lots of different types. All right,
Thank
very
you.
nice. Very nice. Crunch is pretty amazing, right? I don't know about you, but I might even buy a subscription to have it for the rest of my life because, you know, Crunch it is just awesome. Okay, anyways. So where am I going? Oh, yeah, back to the PowerPoint. All right. So let's now turn to slide number 21, which is regression analysis. Now, here's the idea of regression analysis. You've decided that you have a linear relationship. You've taken the correlation, and it's determined that you have a really, really, really strong correlation. The question now is, what do I do with that information? I know that it's linear, and I would like to have a linear equation to correspond to that, but how do I get the linear equation? So regression is about finding the best fit line for a given piece of information. I want to find the best line that I can possibly draw through these points. So if you have the scatter plot in front of you, you might say, oh, that's the best line. And someone else might say, well, okay, I think that's the best line. And someone else, no, I think that's the best line. You can't really do it by hand. Yes, you can use Crunchit on exams and quizzes, no problem. It's very hard to do any of this stuff by hand, especially calculations. So Crunchit will do it for us. We'll see why, how in a second. But for now, let's look at slide 21. Regression analysis. It's the study of the relationships between one or more explanatory variables and a single response variable. We're not going to really worry, I think, at all in this course. Certainly not now, but I'm pretty sure at all about having more than one variable explain the response variable. We're going to have one explanatory and one response. So simple linear regression is a statistical procedure used to determine a model, an equation of a straight line, which best fits the data. Now, unless it's perfectly linear, nothing that you come up with will perfectly fit the data. We're looking for the best possible. Now, the question then becomes what defines best possible, and we'll see, hopefully we'll see what that means in a minute. But when you're done with this procedure, you are gonna have a best fit line. It's gonna be y equals ax plus b. So it's gonna have a y-intercept, and it's gonna have a slope. So if I go back to sharing my screen, let's see if we can find the best fit. Well, it's probably graphics. It's not any of these, not any of these. We have the scatter plot already, but not the best fit. So where would the best fit line be? Regression. Here we go. Regression under statistics. Simple linear regression. The dependent variable is variable 2, right? Dependent, variable 2. The independent variable, variable 1. Display. So let's see if this gives us what we want. Fitted plots. Look at that. Okay. So simple linear regression. Would you say that that line's a pretty good fit to the data points?
Not really, mainly because it only goes through one.
Well, according to math, it is the best fit. So if you would have raised the line and had it go through 3, it would have missed the other 2 by even more, correct? So it's not really how many it goes through. It's sort of like an average of going through all of them. It's hard to describe. Well, when I give you the technical definition of what we're doing when we compute a best fit line, hopefully that will make more sense. But from a mathematical standpoint, this is the best fit line. And if I go back there to regression, simple linear, and I say, give me numeric results. So you'll see here, variable 2, y, equals mx plus b. So notice that the slope is negative, negative 0.1130, negative 0.1130, variable 1 plus 10.82. So that's my y-intercept, 10.82. Y-intercept, 10.82, and slope negative 0.1130. All the other stuff, let's not worry about that right now. We're not ready for that stuff yet. But does that make sense? How to do this on Crunchit to get both the best fit line and the equation of the best fit line? I hope it is. Can you show us how you got that chart again? Do you mean the graph, the scatter plot? Is that what you mean by the chart? Someone's typing. I'll just do it again quickly from scratch. So again, the first thing you do is you put in the data, right? Hopefully you all remember the x values and the y values, variable 1, variable 2. If I want a picture, I go to graphics. I go down to scatter plot. X is variable 1, y is variable 2. I can even label x. The x label is, what was it?
Mileage.
Was the X mileage or was the Y mileage?
The X is mileage and the Y is selling price.
Okay, so I can even go here and label the X as being mileage and Y as being selling price. And I can calculate it. And now it doesn't just say variable 1 and variable 2, but it lists it as mileage and selling price. And then I go to statistics and I go to regression and I say it's simple linear. Dependent is my Y, independent is my X. If I want numerical results, it gives me my equation. And I can go back to regression, simple linear, and this time I want fitted plots. And there it is. Oh, it goes back to variable 1 and variable 2. So I guess it can't do everything, but it does a lot. It gives you everything you need. Pretty cool, huh? I hope you got that, because we're back. Okay, so let's continue. So back to, okay, so the regression, we're gonna come up with this best fit line, and we're gonna understand why it's the best fit line. Someone, I don't know who, said, well, I don't think it's a good line. It only goes through 1 point. And as we're going to see, it's not the number of points that it goes through that makes it the best fit line, but rather a different determination. And we'll get there in a few minutes. In fact, we'll get it right now. It's called the least squares method. So the goal is to find the line of best fit. Hopefully we are all together on slide number 22 now. The goal is to find the line of best fit. Can the line be discontinuous? Someone asks. No, the line has to be a line. It's a line. It can't be broken. So it can't do this and then this and then this. That defeats the whole purpose. The whole idea is that the actual relationship is linear. It's just my data takes into account error. The world is not perfect. Babies get taller as they get older. I know that. And they do it in a predictable way, but there's always going to be some uncertainty involved. It's never going to be exactly perfect. But if I think it's linear, then I'm looking for the line that best describes the scenario, whatever that line is. So it has to be a line. And the question is, how do we find it? So the goal, find the line of best fit. And they keep putting best in quotation marks, because what exactly does it mean, the line of best fit? First of all, notice that we use Y hat. That little caret symbol on top of the Y is called the hat symbol. The line itself, the line of best fit, is labeled by Y hat. Y hat equals A plus BX. That's good stuff. Someone sent me a text. Yeah, I thought I already got you. Yeah, I already got you. Okay. So we define what are called the residuals. A residual is the difference between the observed value and the predicted value. So if I go back to my best fit line here in this example, so let's look at this point right here. This point here is the actual value of Y for whatever value of X we're dealing with. This is the X equals 22 case. So when X equals 22, the actual value of Y is 8.5. But what is the if this line is the actual best fit line, what does the line predict should be the value of Y for 22?
Like 8.4?
About 8.4, correct? About right there. So the residual for this point would then be the actual value 8.5 minus the predicted value of 8.4, approximately 8.1. So this point has a residual. It's positive because it's above the line, positive above the line, negative because it's below the line, about 0, but it looks like a little bit negative, and then positive again because it's above the line, right? So we have 5 residuals here, okay? So what we do for the best fit line, back to the scatter plot, is we take the residuals and we square them because we don't want any cancellation, some negative, some positive. So we take the residuals and we square them and we add them all together and you get a value, right? You get a value. So what we do is we consider every theoretical possible line in existence that you can possibly draw. Do this for every single one of them. and then pick the one that gives us the smallest number. So we are picking the line that minimizes the sum of the residuals squared. In theory, does that make sense? Not how would you actually go about checking every one of the infinite lines possible, but in theory, does that make sense what we're trying to do here? We're trying to calculate the residuals for every theoretical possible line? Can you explain that again? My brain just exploded. Okay. So let me try to do it here on the board. So, suppose you have a scatter plot. Doesn't got to be a lot of points. So you have, let's say, 3 points, like this. And someone comes along and says, I think that's the best fit line. Can you even see that?
Yeah, I can't really see that line. There we go.
Okay, someone says that's, let me get a better marker. This one might be dying a little. So someone says that that's the best fit line. And you say, okay, I'm going to compute the residual. I'm going to compute that. I'm going to compute that. And I'm going to compute that. Negative, negative, positive. I'm going to square them all so that we don't have any cancellation. I'm going to add them all, and I get some number. And someone else says, well, you know what? I don't like that one. I think that's the best fit line. And you say, okay, let me compute the new residuals. The new residuals, square them, and add them all together, and I'll compute that number. And I say, well, my number's smaller than yours, so mine's better. And someone else says, well, that's great, but I have another line that I think might be the right one, and I computed my residual squared, and mine's even smaller than yours. Like, oh, okay, yours is even better. We go through every single line. That means every y-intercept and every slope possible. There's infinitely many of them. We go through every single one, and we check one by one which one has the smallest sum of the residuals squared, and that's the one we pick for our best fit line. The question is, how can you do that, right? How can you check every single one of them if there's infinitely many? And the answer is, that's not actually how we do it. In theory, that's what we're doing. We're checking all of them. The real process is a calculus process. Technically, it's multivariable calculus. I'm not sure if anyone here has taken it or not. Has anyone taken multivariable calculus? I'm just curious.
No.
Well, you're answering for yourself. That's wonderful, but I'm looking for chats whether anyone else is, says yes, but no one said yes. Essentially, it is a multivariable calculus procedure where you are determining via an alternate method which one of those infinite lines is the correct one. The method of least squares was introduced in the 1800s by the greatest mathematician of all time. Anyone know who the greatest mathematician of all time is? Or at least who's generally acknowledged as being the greatest mathematician? I don't think, Angel, I don't think it's you. I know that you're up there, but I took a vote about, and nobody said your name, so I just don't think it's you. Ryan's, it's not me. I'm good, but I'm not that good.
Get the name. Isn't it like a French name?
He's actually
Dermond?
who?
Dermond? Am I saying that right?
How do you spell that?
Einstein.
Einstein was not the greatest mathematician. He might have been the greatest physicist, but not the greatest mathematician. And even Einstein said that Isaac Newton was better. So when Einstein says something, he wasn't always right. I mean, there were times that he was wrong. How many Warzone wins did Einstein have? Thomas Edison was a great inventor, although most people would say that Nikola Tesla was even better. Gauss, someone got it. It was Gauss. Congratulations. Now, did you look that up online? Did you check who invented the least squares, or did you actually know that? They Googled it. Yes, cheaters. It was Carl Friedrich Gauss, the greatest mathematician of all time. To tell you a little story about Gauss, the story goes that on his very first day of school, this was in the 1800s, so they didn't start in kindergarten, but he was, they say, about 8 years old at the time. So the teacher that day was getting a little frustrated with the students and gave them an assignment that he thought would take them all day long to do. And that assignment was to add up all the numbers from 1 to 100. 1 plus 2 plus 3 plus 4 plus 5, right? Something that you can give to a little kid to keep him busy for hours. The story goes that Carl Friedrich Gauss, on his first day of school, answered the question immediately, 5,050. Now, it was not Fermat. Fermat was good, but not great. So now, to add up 100 numbers in a row, in an instant, seems rather impressive. But 1 plus 2 is 3, plus 4 is 6, plus 3 is 6, plus 4 is 10, 15, 21, 28. Even going one at a time, it would still take you a while, correct? So how did he do it? He did the following. He said, what everyone knows, even though it was his first day of school, he said, when you're adding, you don't got to add in order. So what do I first add 1 and 100? When I add 1 and 100, what do I get?
101.
101. What's 2 and 99?
101.
What's 3 and 98?
101.
What's all the way up to 50 and 51?
101.
So he just said you have 50 copies of 101. So the answer is 5,050. Now,
So, can you repeat that?
Well, if you're adding 1 to 100, you're really adding 50 copies of 101. Because the first and the last add to 101, and then the next 2 add to 101, and then the next 2 add to 101, all the way until the middle 2 add to 101.
Oh.
Now, from a mathematical standpoint, like today, this is not really that sophisticated. But when you're 8 years old, and it's your first day of school, and you can do something like that, that says good things. So that's the story. So for the least squares, the one with the lowest number means the one with the best predictions. Yes, yes, exactly. The best predictive power comes from the one with the least squares. It is a calculus way of getting it, but luckily, Crunch It knows calculus. So if you look, so let's go back to the slides. We're on 22. We just calculated. We just said the least squares approach is the one that minimizes the sum of the residuals. If you look at slide 23, we see the same scatter plot, but this time the residuals are actually kind of shown there. Remember, if you're above the line, it's a positive residual. If you're beneath the line, it's a negative residual. Okay? And essentially what we're going to do is we're going to minimize the sum of the residual squared. How do we do that? Well, we let calculus do it for us. However, if you look at slide 24, they give us formulas for the y-intercept and for the slope. So the least squares regression line, also called the best fit line, y hat equals a plus bx. The y-intercept a is given by the formula on the right. And the slope b is given by the formula on the left. Notice that to calculate b, you need 3 things. What 3 things do you need to calculate b? As given in that problem. Look at the formula. I'm not telling you why it's true. Just tell me what it says.
Relation.
The correlation are, what else? What else between the, besides the, so Anthony, you said, does it matter if the residuals are positive or negative since you squared them in the end? Not for this particular application. So when it comes to the, of course, some of them have to be positive and some of them have to be negative for it to be the best fit line. Some are beneath, some are above. But mathematically, it makes no difference. So what do I need for B besides R, the correlation? Just look at it. It's on slide 24, the bottom left. What 3 things do I need? B equals. It says it right there. Just say it. R, what else?
both the y and x values? So s of y and o.
Finish, S of y and
S of x.
S of x. What is S of y and S of x? What are those?
Aren't those like the individual values for whatever you're trying to look for?
Well, I don't know what you mean. You have your data, right? You have all your x values, you have all your y values. So what is S of x and what is S of y? So S sub x is the standard deviation of the x values, and S sub y is the standard deviation of the y values. A few people texted to me, right? Remember, for a sample, we use x bar for average, and we use S for sample standard deviation. So S sub x is the x sample standard deviation, and y is the y sample standard deviation. Yes, no, maybe so? Yes? This is not new. You should have this by now. We've used these symbols before. And then once you have B, what do you need besides B to calculate A? As given in that formula. As given in that formula, what do you need besides B to calculate A?
X bar?
X bar and
Y
Y.
bar.
Y bar. What are X bar and Y bar? What do those stand for? What does that mean?
The averages.
It's the averages. It's the means. It's the sample mean for X and the sample mean for Y. Right? The sample means, the standard deviations, and the correlation. You know those things, you know everything. And now at this point, we have the equation of the best fit line. So if we go back to the previous example, next slide, slide 25, we're continuing on the same example. What you can see here is that they've actually gone and done it. They've taken their R value, their X bar, their SX, their SY, and they come up with a formula y hat equals 10.82 minus 0.113x. Let's share my screen again. And if you see here, what do you notice? Variable 2, which is y, equals 10.82 minus 0.1130 times variable 1 times x. So crunch it gives the equation that these formulas will provide. Does that make sense?
Yeah.
Okay. Anyone not sure what we're doing right now, or why we're doing it, or how we're doing it, or anything else? Where, when, why, how, where, when, why, what, how? Any of those five?
Who?
Huh? And who? Oh. Who? Right. So what's how? Was how one of them? No. How I just made, how I just made up.
With H.
Yeah. H. That's just
Professor?
weird. But there is a W at the end. Yes, question?
I was just wondering, so would crunch it give the least square value?
Yes,
The
it will.
least squares?
Yes, it will. How? Through math. I like that. Yes, crunch it does give it. So in fact, let's do an example. Let's see if I can find another example here. Okay, there's not another example. So let's do our own example. Let's load up crunch it. I'm going to share my screen again. And I am going to clear these results because this is a different example. And let's clear the data. We'll use different data. And what I'll do is I'll take out my textbook and we will find an example from the textbook. Hopefully not too many data points because that just takes a long time. Let's turn to chapter 5 on regression and okay, here's one with 7 data points. That's not too bad, right? But I want to do one that has the answer in the book so we can compare it. So let's do a different one. So that way the answer that's there will know it's correct. Okay, ready? Okay, more data points than I would like, but I can't really find another one that I like. So we'll do this one. All right, so this is example 5.5 in the book. It says, I feel your pain. Empathy means being able to understand what others feel. To see how the brain expresses empathy, researchers recruited 16 couples in their mid-20s who were married or had been dating for at least 2 years. They zapped the man's hand with an electrode while the woman watched and measured the activity in several parts of the woman's brain that would respond to her own pain. Brain activity was recorded as a fraction of the activity observed when the woman herself was zapped with the electrode. The women also completed a psychological test that measures empathy. So, will women who score higher in empathy respond more strongly when their partner has a painful experience? First, I'm going to stop sharing for a second to see if you guys understand what I just read as the example that we're going through. So, women took the woman in the study took a psychological test to measure empathy, and then they also watched their partners get zapped with electrodes and had their brain activity measured to record whether they were feeling empathetic during that process. So do you guys think that there should be, how fun, right? Do you guys think that there should be a correlation here? And if there is, positive or negative? What do you guys think? Anyone have an idea? Negative. Do you think someone who scores higher on the written portion would score lower on the actual measured portion? That's what a negative correlation means, is one goes up, the other one goes down. Someone says no correlation. Someone said it does not sound ethical. Well, if everyone volunteers and they volunteer, I mean, I guess it's ethical. But anyways, so let's go to share screen. And let's put it in here. So variable 1, empathy score, 38, 53, 41, 55, 61, 62, 48, 43, 47, 56, 65. I think I missed one. 36, 38, 53, 41, 55, 6. Oh, there was a 56 in there. I'll put the 56 now. 19. Wow, 19. You suck. All right, 61, 32, and finally 105. So the 38 scored a negative 0.12. That's the brain activity. That means, I guess, they were happy, maybe? What a relationship that one was. 53 is 0.392. 41 is 0.005. 55 is 0.369. 61 is 0.415. 0.107. 0.506. 0.153. 0.745. 0.255, 0.574, 0.016, 0.21, 0.722, 0.358, and 0.779. Okay. Oh, we didn't need that. Okay, so I don't know how to delete a line here. Edit. Delete selected. Okay, I don't know how. So let's take a look at the scatter plot first. It's not mileage and sales selling price anymore, so let's get rid of that. And let's calculate it. And that is the scatter plot. So when you look at that scatter plot, does that look like it is linear?
No.
No.
Certainly doesn't look that way, right? However, we have to keep in mind that the eye can be, I mean, we can't always tell just by looking because of levels of zoom and whatnot. So nothing beats actually calculating it. So let's go to statistics. This time we're going to go to, first let's look at the correlation. I'm curious what the correlation is. 0.5151 correlation. So what does 0.5151 tell us in terms of the strength of the linearity?
It's moderate.
Moderate. Okay, well, it's certainly not strong, but it's moderate. And in fact, it's very close to weak, right? So it does fall in the moderate realm, but it's pretty close to being weak. Because remember, the cutoffs are not set in stone. Okay, then we go to simple linear regression. And we want to do a fitted plot. Let's see what their best fit line is. Does that seem reasonable as the best fit line?
Yeah.
Yeah, it seems fairly reasonable. And then we go back to statistics, and this time let's compute the equation of the line. And we get a negative y-intercept, although very close to 0, but a negative y-intercept plus a very small positive number. Now, keep in mind, if you look at the scales of these x and y axis, the x-axis is going from 25 to 100. The y-axis is going 0 to 0.8, right? So you got to be very, you got to reckon that the scale is off so that these numbers might not seem obvious. But when I look in the book to this problem, I get y hat equals negative 0.0578 plus 0.00761 x. So the book agrees. And those are the steps for plotting not only the scatter plot, the best fit line, but also coming up with the correlation and the equation of the best fit line. It says maybe if you change the scale, someone said. I don't know if you can change the scale. I don't know if that's something that I have the power out in doing, but does that make sense for how to do these types of problems?
Yes.
All right, why don't we take a 5-minute break, and when we get back, we will continue with them and see how we can use best fit lines to actually make predictions. So it's 5:03 on my computer. Let's be back at 5:08. So try to be here in 5 minutes.
I have a quick question.
Yeah.
So Y bar is the sample standard mean?
Y bar is the sample mean of the Y values.
Okay, thank you.
Welcome.
Professor,
Yes.
so you go to crunch it, you hit statistics. This is after you've done the fitted plot.
Okay.
Where do you click after that?
So let's take a look. So I go into statistics.
Right.
And now there's two things that we've done so far. There's correlation
Uh-huh.
and there's regression.
Correct.
If I want just the correlation, I go to correlation.
Okay.
If I want any of the other stuff, I go to regression and then simple linear regression.
Okay.
And then this part here, the display, I can do the fitted plot, which is the line, or the numeric results, which gives me this.
Okay.
Make sense?
Yeah.
Okay.
Thank you.
You're welcome.
So with slope, I'm kind of like having a hard time understanding, like translating it, I would say, Because I'm so used to seeing the equation of a line a different way, slope.
Wait. How are you used to seeing the equation of a line?
So y equals mx plus b.
So rearrange it. So it's y
Right.
equals 0.0076x minus 0.05775.
Yeah, and I got that.
Okay.
But the slope, so usually like the slope is y2 minus y1 over x2 minus x1.
But here's the thing. We don't have points on the line. We're not taking two of the scatter points and using that to compute the slope.
Oh.
Okay, these points are not on the line. None of them are, unless by coincidence one of them happens to be on the line.
Oh, so it's just by chance then.
Yeah, if a point happens to line a line, it's like, okay, that's quite a coincidence. In general, they're not going to.
Oh, okay, okay.
The approach by which the computer is calculating the slope is not y2 minus y1 over x2 minus x1.
Okay.
Okay?
Yeah. All right, that makes sense.
No problem, no problem. Oh, 5:09 already. Okay, are we all back? Kind of lost track of time there. How do I spotlight myself? Cancel the spotlights. Spotlights. Oh, there we go. Okay. All right, so let's now turn to slide number 26. We are continuing with this car example. of mileage versus selling price. I guess mileage per gallon is probably what they mean by that. Let's go back. Where do they define it? Mileage in no, not mileage per gallon. It's how old the car is, right? How many miles it has. Makes a lot more sense. All right, so we're on slide, what do we say, 26. Okay. So, the more mileage that the car has, probably the cheaper that it is. So we expect to have a negative scatter plot, right? As the number of miles goes up, the other thing goes down. That seems very reasonable. And it says to graph, plot any 2 points on the data line and connect. Well, don't even listen to that. That's what we do when we don't have Crunch It that can do the best fit line for us. So this whole slide 26, just completely and utterly ignore. This is just stupid. I don't know who put this PowerPoint together. That's horrible. There's no need for that when you have Crunch It that can do it for us. Unless they're just trying to point out that their equation that they get by using 2 points is close to the true value, which it is, but oh, wait a second, never mind. I misunderstood. Sorry. They're not saying take 2 of your data points. They're saying once you've graphed your best fit line, you can calculate the equation of the line the usual way by taking 2 points on the line. But again, we don't need to do that because we have Crunch It who gives us the line. So ignore this page, you just don't need it. Let's look now at slide number 27. Slide number 27 is a very important slide. It talks about the coefficient of determination. R is the correlation coefficient. R squared is the coefficient of determination. And the question is, what exactly does it determine that it's called the coefficient of determination? So let's go to the following example. Consider the following situation. If I calculate the heights of children as a function of their age, I expect to have a positive correlation, correct? As children get older, they get taller, right?
Yeah.
It seems reasonable. Will all the points fall on, even if it's not linear, even if it ends up being a curve, do I expect all my data points to fall perfectly on that curve? No. So the y values of all those data points are going to be different. Y values being, x being their age, y being their height, right? The y values are going to be different. But there's 2 reasons, 2 completely separate reasons why the y values are not all the same. What are the 2 completely separate reasons why the y values are not going to be the same for every one of my data points? I want 2 reasons. Why are the y values different? Why are the y values different?
You're saying with the height versus the age?
Yeah, so ages, different ages, different heights. The heights are not all going to be the same, right? The y values are not all going to be the same. So I want 2 reasons why the y values are different when I look at all my different points. 2 completely different reasons.
Well, aren't there like I'm 19 and let's say other 19-year-olds aren't all the same height as me.
Why not?
Genes.
Okay. Genes, genetics, real life, nature versus nurture, call it what you will. But there's always going to be fluctuation because of real life circumstances, correct? I'm sorry, I had scrolled up, so I didn't see people respond. People grow at different rates. The age, the height can decrease, right? There's a lot of nutrition, right? Certainly lots of real life factors. What do I have against Harry Potter? Are we still talking about that? I can't go into it right now, okay? We will talk about it at some later time. when I'm in a better place. Okay, but for now, the question is, why are the y values different? All of your after class we can talk. All of your answers so far. Thank you, Ryan. Now that's what I'm talking about. It's because I haven't opened up my third eye. You want quality reading? That's what we're talking about. But anyways, all of your reasons so far are basically the same reason. The y values are different because of real life situations, genetics, ethnicity, nutrition, nature versus nurture, etc. But you're missing the other reason why the y values are different, why the heights are all different. Because the ages are different. If your x values are different, your y values are probably going to be different, right? As your as your age increases, your height will increase. Even besides the randomness that is inherent in nature, just the fact that your x value is changing should imply that your y value is changing, correct? So there's two reasons why the y values are going to be different. One, different x values, and two, we can encapsulate all of it by saying the randomness of real life. So what does r squared tell you? So let's go back to the slide 27. R squared tells you the proportion of the variation in your y values that is dependent upon variation in your x values. So that means if we look at the car situation where my correlation was negative 0.96, if I square negative 0.96, I get 0.9216. That tells me that 92.16% of the variation in y values is a result of the variation in x values. And it's the other 7.84%, whatever it is, that is due to randomness of nature. Okay, the r squared value tells you what percent of the variation is due solely to changing your x value, and contrastly, or in comparison to the remainder of it, which is due to the randomness of nature. So if I have a very high r squared value, that tells me, so someone says, so COD is the correlation. No, r is the correlation. COD is the correlation squared. Mathematically, they're different things. R tells you the correlation. COD, so r squared is the COD, is the coefficient of determination. It tells me what percent of the variation in my y values is the result of the variation in my x values. If you have a very high r squared value, it tells you that randomness of nature had very little to do with it. If you have a very low r squared value, that means randomness of nature had a lot to do with it. So if you look at this example, the last paragraph, 8% of the variation in selling prices is left unexplained. This remaining variation is presumed to be due to other variables not considered. The condition of the car, the age of the car, the color of the car. Some people like red. Some people hate, chartreuse, or, I don't even know if that's a color. I heard it once. I don't know. The point is that there could be other reasons why that we are not looking at. In the case of the height versus age, we're not looking at nutrition. We're not looking at genetics. We're not looking at any of the other things that might play a role. We're looking only at age. Age explains this percent of the reason why heights are different. Why are the other heights different? Lots of other reasons that we're not getting into. Does that make sense for what r squared is telling us? I hope so. So let's look now at slide 28. Units and prediction. So once you have the best fit line, the question then becomes, can I do anything with the best fit line? What's the point of having it? And the answer is you can do a lot with it. In fact, what you can do is you can predict using it other y values for x's that you might not even have. Why would I want to do something like this? Well, let's think about it. Suppose I'm interested in opening up a pizza shop. And I decide that the best place to open a pizza shop is right near a college, because colleges have lots of students who, I mean, everyone likes pizza, right? There's not a single person on the planet that does not like pizza. That person does not exist. And if they say they don't like pizza, they're lying. They are a secret pizza lover. You know it's true. You know it's true. So I decide college students is the perfect age because pizza is relatively cheap. It's tasty. It's quick. You can study and eat at the same time. I'm going to open a pizza shop. But I don't know exactly the best place to have my pizza shop. So I'm going to do a study, and I'm going to look at all the pizza shops around all the cities in America and calculate their revenue based upon, for example, how far they are from the nearest college. So pizza shops near colleges, pizza shops not near colleges. Let's compare their revenues and see if distance from college has any correlation to how much revenue those pizza shops earn. Does that seem like it might be something worthwhile doing if I was really interested in opening up a pizza shop?
Depends on how good your pizza is.
Well, okay, so there's that to go with it too, right? How good is my pizza? Now, I've had some good pizza and I've had some bad pizza, but at the end of the day, pizza is pizza, and therefore it's all good. Except for microwave pizza. That's not good. Don't ever do that. Although someone gave me a trick recently. Have you guys tried this? The water thing. Have you guys ever heard about this? When you reheat pizza, you put a cup of water in the microwave at the same time. It's got something to do with the whole microwave, the way it works and whatnot. And apparently the water stops the pizza from...
I thought it was a wet napkin.
Well, yeah, I guess you can do that too, but I don't know. I'll just, whatever. Rude my thunder there. I thought I was like coming up with something amazing here. Anyways, just dunking it. Oh, God. Oh. Someone just said just dunk it in water. Just dunk pizza in water. You know what? Don't ever text me again. You can't text me anymore. That's just, you just ruined my day. You just ruined my day. I don't like pizza. No, see, she's a pizza lover. She loves pizza. She's just, I don't believe it. Yeah, fail them. That's right. You don't even come back. You're done. You got an F. Don't even bother coming back. Fail them all, she says. Fail them all? What, people don't like pizza? What are you saying? I don't know what you mean. Fail them all. Is that, what? That's horrible. Anyways, let's move on. So what I can do is I can make this scatter plot, and then I can make my best fit line. And suppose I feel that there's a really strong correlation between distance from pizza shop and revenue earned. And I find this great location that's a certain distance from the nearest college. How can I use my best fit line to predict what my revenue is going to be? So the answer is, once you have your best fit line, your y hat equals mx plus b, I can just plug an x value into that, and my y hat's going to be my prediction. So I use the points that I'm given to find the best fit line, and use the best fit line to find other y values for points that I wasn't given. Let's do an example to illustrate that. So let's look at slide number 29. We have our car example again. We have our best fit line, y hat equals 10.82 minus 0.113x. And someone says, okay, what if x was 28? I found a great car. It has 28,000 miles on it. I'm wondering, what is a good price for this car? Well, I go to my best fit line, which tells me selling price is a function of mileage. And I plug 28 into my x. And I just do the math, and I get 7.66. And that tells me that an appropriate price for that car should be in the vicinity of $7.66 thousand. Does that make sense?
Yes.
And if x was 20,000 miles, so that my x should be 20, because remember, it's in units of 1,000 miles, I would plug in 20, do the math, and get my prediction of 8.56. So what we do with the best fit line is we make predictions. We plug in x values and we calculate y values. Seem reasonable? I hope so.
Yeah.
So let's look at slide number 90. And the slide, sorry, not 90, I don't know why I said that, slide 30. And slide 30 gives me an example of a regression line. We have number of children and number of cars. So one family has 4 children and, oh, I see. The formatting is a little off. The bottom line and the top line should be, the bottom line should be moved 1 unit to the left, and the top right to, or the top line 1 unit to the right. You see what I mean by that? How the formatting's a little off there? So number of children 4, how many cars go with it? Flush. 3, so if you look at the scatter plot, we have 4 comma 3, that's a red dot. The next one is 1 comma what?
1.
1 comma 1, we have a red dot. Then we have 5 comma
3.
3, we got a red dot. Then we have 2 comma 2, we have a red dot. And we have 3 comma 2, we have a red dot, right? We have 5 red dots. So let's just get more practice with this. Let's load it up and go to crunch it. Let's remove all this data here and all this stuff. And there's got to be a way. There's got to be a way.
Go to File, New, and it'll clear everything and make you a new one.
Boom. Love it. Thank you. So let's put our data in here. 4, 1, 5, 2, 3. And 3, 1, 3, 2, 2. And then we go to graphics and we make a scatter plot. And I really don't care about the labeling right now. I want to show the points. So let's calculate. And that's my scatter plot. Does that look fairly linear?
Yeah.
Yes.
All right. And now let us go back to statistics and let's calculate the correlation and see what that is. We get 0.9449. What does that tell me about the correlation?
Very strong.
Very strong, right? Right, very strong. And we go to statistics again. This time we do regression. We do simple linear regression. We want the numerical results. And we also want the fitted plot. Okay, so there's our best fit line, and there's our correlation, and there's our regression line. Y equals mx plus b. What's the slope here? What's the slope?
0.7000.
The slope is next to the x, isn't it?
0.5.
0.5, right? Y equals mx plus b, correct? Right?
Wait, can you explain that one more time, please?
Well, what's the equation of a line? What's the equation of a line? Y equals?
mx plus b.
Mx plus b, but it could also be b plus mx, right? You can always switch the order of the two things that you're adding, right? Correct?
Yeah.
Well, in this case, the way the Crunchit program puts the equation is they do b plus mx because the 0.5 is times the variable 1, and the variable 1 is x. So the slope is 0.5 and the y-intercept is 0.7. Do we agree with that?
Yeah.
Now let's interpret what this means. Before we finish the question, let's interpret what this means. This means that for every extra x value, for every extra child that I have, how many extra cars am I going to have on average?
Half.
A half, right? As x goes up by 1, y goes up by 0.5. So that means every extra child overall, as a general rule, corresponds to another half a car. Doesn't mean you chop it in half, it's only an average. But the more important one is that if I have 0 kids, how many cars am I going to have now on average?
0.5 or Not 0.7.
Negative?
0.7. Now look at the y. Remember, the y-intercept is the value when x is 0. I have some text here. Yeah, so some people responded. I just didn't see it until now. But yeah, the y-intercept is the value when x is 0. So it doesn't go that far because it only makes my line between my leftmost and my rightmost point. But if I were to continue along to when y is 0, here or so, it would be about 0.7. That's what it's claiming. So that means, and again, look at the scale here. Each box this way is 1, but each one this way is 0.5. So the scales are off. But this tells you that what the slope is. It tells you how y changes as x changes. And the y-intercept, which tells you what y is when x is 0. But anyways, back to this original problem that we have on the slide. This is slide number 30. So as you can see there, the scatter plot matches our scatter plot, correct? Seems very close. Yes?
Yes.
Yeah.
Okay. And the question is, if I were to have 2 children, hold on one second, guys. I'm still teaching upstairs. Oh, it's okay. You can still talk, but just it's a little. Thank you. You guys are. Thank you. Okay. She's leaving tomorrow, so they're having a dinner.
Oh, she's leaving tomorrow.
Yeah, it's just we were a little loud, so yeah, she's leaving tomorrow. Okay. So if I have 2 children, what does the line predict would be the correct number of cars? Well, I just plug x equals 2 into my formula. What do I get when I plug x equals 2 into my formula?
1.7.
1.7. 2 times 0.5 plus 0.7, 1.7 cars. And if I had 4 children, it would be 2.7 cars. So it's very predictive, right? Very predictive. Okay. This one, oh, it says interpret the slope. Slide number 31. Interpret the slope. We already did that. The interpretation of the slope is, again, for every increase in 1 in the x direction, I would increase in 0.5 in the y direction. So that means that for every extra child that I have, I would have I would have a half an extra car. So 2 children, get a new car. 2 more children, get a new car. Let's see. So I'm looking ahead at what comes next. Next seems like it's a nice section which is all connected. So this is a good time to stop. And we will finish this slide and start the next slide on Tuesday. It is also the end of week 4. Let me check the syllabus about whether or not we should expect to have a test soon. Hold on a second. I think the first 5 chapters is a really good stopping point for a test, but I don't have anything from my boss telling me that we're going to have a test soon. So does that mean chapter 4 homework is not due next Tuesday? That's correct. You always get a full week from when we finished it. Well, 4 we finished. 4 we finished. 4 is linear correlation. That is done, and the homework is due next Thursday. 5, on the other hand, is regression, and 5 we have not finished. So 5 you'll have till the following Tuesday. Okay, does that answer your question?
Chapter 3 is due next Tuesday, right?
I pushed off chapter 3, but till next Thursday, yeah, or next Tuesday, I think. But chapter 4 will be due a week from today. I am looking. I'll write this down. So schedule exam 1, and we should have another quiz anyways, because I got to be in line with the other classes. So why don't we plan also to have a quiz on Tuesday? What chapter do you guys want the quiz on? Any preference for what chapter it should be on? Chapter 2. What was chapter 2 about? All of them. Yeah, nice. What was chapter 2? Anyone remember? Wasn't the first? Oh, mean and median, stuff like that. Okay. Schedule exam 1 and quiz 2 on chapter 2 on Tuesday. Okay, so we will have a quiz on chapter 2 on Tuesday, and I will schedule exam 1. Is there a way for us to look at previous homework and practice quizzes? Does it turn them all off so that you can't review them? Is that what happens? Yes. All right, I'll look into that. Let me write that down. Check for reviewing old homework. So the exam is not anytime soon. I think the exam is going to be soon. We're just finished the 4th week. And if we have 2 exams, it's roughly 5th week, 10th week. So we should probably expect an exam relatively soon. But whatever day I will tell you about it, you'll have at least a week from that time. So if I tell you today, the earliest it can be is Thursday, but I'm not telling you today. If I tell you on Tuesday, the earliest it can be is the next Tuesday, and so on. Okay, so you'll always have at least a week. But we should certainly have a second quiz because the other sections are doing quizzes, and we should too. And it's almost the weekend, so I'll be putting up your homework scores if I haven't already, and trying to catch up. So that's it for today. I'm going to stop recording.